So now let's see if we could display some ASCII character data from a message stored in audio format on the cassette drive in Kansas City Standard. And it's working. And here is the text coming through on a 8x8 LED matrix. So stay tuned if you want to see how you can translate a UART signal into a 2D display. So the last time I made this cassette tape data decoder and encoder, the encoder nobody really watched, but what I got from that tape drive is you can see the UART data, which is shown in the yellow tracing here, and continuously every time there's new data, it's synchronized and it gets put out. But other than displaying it on a laptop through an FTDI cable, what can we actually do to this data to display it better? So here's the schematic diagram of the encoder circuit, where I used a bistable 555 timer and two CD4017 counters to basically count out the bits and synchronize it with a 300 bits per second signal. The UART data needs to be displayed in a way and be able to be output in a parallel fashion. So in order to do this, I used the serial input parallel out shift registers. Basically, in this way, you take a UART signal, which is serial data, least significant bit first, and turn it into parallel data that you could do something with. And ultimately, I want to display this in the ASCII format. And so in order to get the timing right for the shift registers, I basically use the inputs for the serial clock and the latch clock, the register clock, from the CD4017 1 and 2 counters respectively, in order to lock the data. Now here's the setup. So now I have the output of this encoder going to show data at the same time because it uses the counters. And so when I take a cassette drive, this is my Walkman, and I press play from this, that goes into this wire from the headphone jack, goes to the decoder, which sends the decoded data over to this, which not only encodes it in Kansas City Standard audio, but also can take serial data and make it into parallel output data in these little LEDs. So what I was looking for before with the oscilloscope, now I don't need an oscilloscope because I could see the data, but if I could trust the data, then it's going to be even better. So let's turn this on and see what happens. So let me press play. And now here's the UART data coming in. Space bar. You could always spot the space bar. These two bits are high in lowercase letters, that's a space. Uppercase letters, only this one is high. And there it goes. Let me stop it. And that's it. So now I'm testing the data against the backdrop of the oscilloscope in order to make sure that the data is in fact valid that comes out of the shift registers. And so here I'm going through the whole entire alphabet, being input as UART data out of my laptop through an FTDI cable. And I'm trying to see if the oscilloscope values match. The least significant bit in the data on the LEDs is on the right, but on the oscilloscope is on the left. So now what do we do with this data? What does it mean? So this is the ASCII table of characters. It's an American standard. And as you can see, the higher top bits code for the column, and the lower bottom bits code for the row of each character. Each character is represented as a 5x7 dot matrix in this case, but different fonts have different dot matrices. And as you can see, numbers go down, count in binary. The higher order bit, most significant bit, is always 0 in standard to correlate with the UART standard. And so we're going to try to implement this. And how are we going to do it? I'm going to use an EEPROM, basically a read-only memory. So let's see how this works. So in order to use this EEPROM, this is a 32 kilobyte or 256 kilobit AT28C 256. First, you have to get rid of the software data protection, which came on every single one that I bought. And this is the pinout, and it has a total of 15 address pins, and the write enable and the output enable and the chip enable are all active low, and the data outputs are at the bottom, pins 11 through 19. And the other address pins are sort of strewn about. And so once I did that, then I can actually program it. So for example, I've put in some data values already. I have the output enable, which is tied high through this 100K resistor, and this is the write enable, and I have that tied high to 100K resistor. So in order to output the data here, I have some data stored at address 0 and 1. And these first 3 black wires are the first 3 address lines. So at address 0, I put that in there, and I press the output enable, which grounds it, and I have that now. And when I put it to address 1, by putting this wire into positive rail here, I get the opposite. This is hex AA, and the first one was hex 55. And so these come pre-programmed to, when they're erased, to all ones across every address line. So anyways, we're gonna now be able to program this by hand. So if I wanted to program address 1 now, which we're currently at, if I wanted to put, make it an 80, a hex 80, which is the most significant bit high. All right, now everything's grounded except for that one. So let's try to write enable that. Now, if I unplug these, I should have on the output enable that 1 or 0. It's 10000000, which is hex 80. All right, so that worked. So now, based on that, we can program this whole thing by hand, which is going to be a pain in the ass, but I'm going to do it nonetheless. So here goes. So in order to illustrate how each ASCII character is stored in the EEPROM, I'm going to use the letter A as an example. So the letter A, the UART signal for this is 01000001. And if we zoom in on the letter A character, you can see which bits are on and which bits are off. So if you took a 8x8 LED matrix like this, where the columns are all the anodes and the rows are all the cathodes controlled by resistors, which you can ground, you can come up with a way to promote the signal using the top address bits from A to 10, or from A10 to A3, and A0, 1, and 2, controlling the different rows, because there are 8 total rows here, and we can have 8 different rows of data corresponding to each of the lit bits or unlit bits. So in the case of the letter A here, for example, the first address, which is the top row, address 0, would have the bit values you can see there, and each subsequent row would have the other address values. So hex 22 for address 1, address 2 or address 010 is also hex 22 or 0010, 0010, and so on and so forth, to store all of the data. So here I have the CD4029 binary up counter counting away at the lowest 3 address lines in binary, basically from 0 to 7, and you can see the row data being displayed on the 8 LEDs. So the first thing I'm going to do is build an 8x8 LED matrix display where I have all the anodes of the LEDs connected together in each column and all the rows connected in each column. The rows are basically connected to transistors, which when given a positive signal to the base will ground them and allow each row to light up whenever that transistor is signaled, and whatever data in the columns is going to light up as well. Now if you can ground all of the rows independently of one another sequentially and fast enough, you get persistence of vision. So now to illustrate this concept, I have here the first column connected to 5 volts, and the rows, which are the transistors, I have signaled to go to ground sequentially by a CD4017 counter, which is being clocked successively at a higher rate until you have persistence of vision. And as you can see, this happens at about a clock rate of 480 hertz, which corresponds to 8 rows when divided by 8 is about 60 hertz, which is the conventional rate for persistence of vision, where the human eye can't tell that each row is being cycled individually, sequentially. So now, since we have the lowest address lines A0 through 2 being cycled through by the binary counter, the CD4029, we also have to have the rows of the display counted off in a synchronous fashion, basically by a decade counter. And we're using a CD4017 here to basically turn the rows off and on. So now you can see the individual rows of data for the letter A lighting up sequentially using this timer and synchronized with the address counter. All right, let's see how this works out. I have a potentiometer here to control the clock speed, and this is coming from the EEPROM. And let's see if the display will work. I'm going to increase the clock speed. There we go. The letter A. So, to do that, I'm going to take this 1 microfarad capacitor out. I'm just going to make a mess of and I'm going to replace it with a 27 nanofarad capacitor. And there we go. And I can really see the A. It's 224 hertz. frames per second. So at this address on the EEPROM, the address lines are in white here, and you can see the most significant bit here is 0. They're in order, so 0, 1, 0, 0, 0, 0, 0, 1. And I have the 3 lowest address lines cycling through a binary counter at 60 frames a second. And you can see here that that makes a letter A. So now after painstakingly programming this, I have an A. And if I change this address line and make it 0, and this one 1, and then I press the output enable, I get a B. And that's in the UART location for B. So in this way, here's the row data for the capital letter ASCII characters, which I painstakingly input into the EEPROM. And here they are being tested by me manipulating the various address lines in order to get to the corresponding characters. And you can see here the W, X, P, Y, just as an example, R. So now we're going to do all the lowercase letters in a similar fashion. So here's all the row data for the font that I designed in order to display the row data for the lowercase ASCII characters. And there's an A, and there's a B, and this is testing it out. Here's a C, a little g, lowercase g, E, so on and so forth. I'm not going to look at all of them now because manipulating the address lines by hand is a little bit painful. So we're going to test it all out in a second using my laptop with an FTDI cable outputting UART data. So here I'm typing in letters, which the output of which is going through a USB to UART cable, which is going and being decoded and going to the ASCII EEPROM. And I've encoded 26 uppercase, 26 lowercase, and the numbers 0 through 9. And they all work lovely. So now, to get rid of the laptop, I've taken this cassette tape drive Kansas City standard audio decoder, and I've conveniently placed it in a housing, which involves a cassette tape case. And what I'm going to do is I'm going to play data from the cassette drive, decode it into UART, and see if it displays. This data is coming out at 300 bits per second. And here's the message. Hello, my name is Igor. So as usual, I'm going to leave you guys with the complete schematic of the entire circuit and then display and how the EEPROM is connected. And here's a secret message from cassette tapes stored in Kansas City Standard.